Welcome back to the Psyche and Singularity series. I've been going over my book, Psyche and Singularity, Jungian Psychology, and Holographic String Theory. In the previous videos, I've been going over the history of physics that led from Newton's theory of gravity to the theory of gravitational singularity inside a black hole. And the two major theories of physics in the 20th century, relativity theory, the special and the general theory of relativity, which is Einstein's theory of gravity, and then the theory of quantum mechanics, as I discussed, they don't work in each other's domains. You would think there's one universe, or at least there's one natural expanse. If there's a megaverse, at any rate, there should be one law of physics that describes everything at the largest scales and at the smallest scales. And the idea of a singularity requires that you have a law of physics that can cover something that is both infinitely heavy, or at least tremendously dense, with infinite amount of gravity, or next to infinite for those who are rejecting the concept of infinite gravity, and something that's also the smallest thing possible. So a singularity requires quantum mechanics and general relativity, the theory of gravity, to work together. And that is where string theory comes in. And the crisis that forced Leonard Susskind to develop, along with Gerard 't Hooft, the holographic interpretation of string theory was Stephen Hawking's claim that information that falls into a black hole is permanently lost from the universe. That claim, if it was true, would violate the most fundamental principle of physics, according to Leonard Susskind, the principle of the conservation of information, even more fundamental than the conservation of energy and mass. He explains that all of the information describing all of the trajectories into the past and into the future of every particle in existence must be capable of being retraced, at least theoretically. Not necessarily practically, but for example, if you exploded a bomb, every particle of gas and every fragment of that bomb, not only should all of the energy and the mass still exist, just in a different form, but all of the information describing the trajectory of each bit of that bomb should theoretically be capable of being retrieved and retraced. We saw Laplace mention the same theory in relation to Newton's theory of gravity, that a cosmic mind, if it could know the position and the velocity of every particle in the universe at any given instant, then it could infer the position and the velocity of every particle into the infinite past and into the infinite future. So the past, the present, and the future would be present to that kind of a cosmic mind. And Einstein's theory of general relativity and special relativity implies the same thing, that each moment of the past, the present, and the future coexists. No information is lost. As a matter of fact, everything is predetermined in this eternally fixed sequence of events. Einstein didn't like quantum mechanics because it says you cannot know the position and the velocity of a particle at the same time. The more you know of one, the less you know of the other. The more you know of its position, the more it acts like a particle. The more you know about its momentum through space, the more it acts like a wave. They're mutually exclusive but complementary perspectives of the same thing. But as Susskind explains, just because quantum mechanics tells us that it's impossible to predict exactly where and when a particle will appear, the information is nevertheless fixed in the universe. Quantum mechanics does not violate the principle of the conservation of information. There's no cosmic mind that could predict where every particle will be exactly in the past and the future, but that information is there. You can't determine what it is, but it is already determined. So Stephen Hawking said, well, but not in a black hole. Something that falls past the event horizon of a black hole. And then Stephen Hawking came up with the idea of Hawking radiation. So what that is, and this is an important concept, according to Stephen Hawking's theory, the quantum vacuum, as we discussed in the previous videos, is made of constantly emerging virtual particle pairs, a photon and an antiphoton. Every particle and its antiparticle are constantly emerging out of the quantum vacuum and then almost immediately annihilating each other. And that creation and destruction that's constantly going on at a phenomenally rapid rate, 10 to the negative 42 seconds, every 10 to the negative 42 seconds, the Planck unit of time, the entire universe is being created and destroyed. So these virtual particle pairs, according to Hawking, if they emerge at the event horizon of a black hole, one of them can get sucked into the black hole, but the other can escape. And if it emerges just at the razor's edge of the event horizon, then the particle that escapes from that annihilation of union with its antiparticle will carry off. It's as if it's evaporating the black hole, according to Stephen Hawking, that the black hole is absorbing the antiparticle, and therefore it's shrinking, and a real particle is escaping. That real particle isn't information from inside the black hole, says Stephen Hawking. But nevertheless, the black hole is shrinking, the Hawking radiation is emerging, but when the black hole finally reaches a terminal point, it just disappears and explodes into photons. Then all of the information that was locked in that black hole is gone. So the principle of information conservation is violated by black holes. Leonard Susskind heard Stephen Hawking give that presentation in the attic of a motivational speaker in San Francisco, who this motivational speaker had a soft spot for physics, so he would sponsor physics conferences. So that's where Leonard Susskind heard Stephen Hawking say this, and he realized that this was the great paradox that could shape the future of physics. And he knew he had to save the principle of information conservation from Stephen Hawking's assault, but he didn't know how to do it because everything Hawking said made sense. But Leonard Susskind teamed up with Gerard de Hooft, and the theory that they came up with, to make a long story shorter, is the theory of holographic information conservation, and it's based on string theory. So I'll start at the end and then go back to explain what string theory is, but here's what Leonard Susskind says. The information that's falling into a black hole is made of strings, not point particles. So according to quantum mechanics, atoms are made of electrons orbiting a nucleus of neutrons and protons. And those are made of even smaller particles called quarks. But according to string theory, all of those particles are made of even tinier filaments of energy, elastic threads of energy that are much, much smaller than a quark. There's no technology capable of observing these fundamental strings. They're down 10 to the negative 33 centimeters, the Planck length. That's how tiny they are. But down there, at that tiniest level, is the quantum vacuum, where all of this violent creation and destruction of virtual particle-antiparticle pairs is occurring. And that causes these elastic, tiny, tiny threads of energy to spread out all over the expanse of the cosmos. But, so the information of which any object falling into a black hole, that information is made of these fundamental little threads. These threads, as they approach the event horizon, from the perspective of someone watching from outside the black hole, the threads would get smeared around the event horizon. And then as the Hawking radiation emerges from the quantum vacuum, one of the particles gets sucked into the black hole, the other one, just on the razor's edge of the event horizon, leaks back out into the observable universe and carries with it, like a letter carrier, the information that gets smeared out on that event horizon. However, if you were following the information as it goes past the event horizon, from that perspective, that information would be gone, irretrievably lost to the observable universe. You wouldn't be able to escape the inward tidal flow of space-time. because it surpasses the speed of light at the event horizon. So that's the holographic principle, that information is conserved on the event horizon, and the idea that it is released from one perspective and swallowed from another is called black hole complementarity. We saw complementarity for quantum physics. If you observe which slit in the two-slit experiment the particle goes through, it goes through as a particle, and it lines up directly behind one of the slits. If you don't observe which slit the particle goes through, it goes through as a wave of probability, and then it collapses into a particle at one point on the detector screen, but it could be anywhere on that detector screen. And when you see the accumulated effects of those electron hits over time, it gradually assumes the same wave pattern, the interference pattern that a wave would have created if it had gone through those two slits at once, spread into two smaller waves, interfered with itself, and created an interference pattern. That's the complementarity of quantum mechanics. So Susskind applied that to the black holes. If you are following information past the event horizon, it's lost to the universe. But if you're watching from outside the black hole, the information, which is made of these fundamental strings, gets smeared out around the event horizon, then leaks back out with the Hawking radiation. So that's black hole complementarity. And the inside-out black hole Big Bang universe, so a black hole space-time contracting toward a singularity, and where the contraction reaches the speed of light, that spherical border is called the event horizon. So the Big Bang is a black hole in reverse. Instead of contracting toward the singularity, it's expanding away from it. And where the expansion of space-time reaches the speed of light, the outward expansion, that's called the cosmic horizon. And information, if you're looking at the cosmic horizon from inside the universe, as you see an object expanding towards that border, the fundamental strings of which it's made would get smeared out all around the inner sphere, the inner circumference of the universe, and then it would be projected back into the universe with the cosmic microwave background radiation, the echo of the Big Bang. And that the past, the present, and the future, every bit of information that constitutes the entire temporal trajectory of the entire universe, all of it is located at each point, according to holographic string theory, of this encompassing sphere, and then it radiates in with this cosmic microwave background radiation. These threads of energy radiate back in to create the three-dimensional objects we perceive, which are really, according to Susskind, like holographic images. We live in a holographic movie, a moving holographic series of images, all of the information of which is recorded at the cosmic horizon. So that is called cosmic complementarity. If you were watching from inside the universe, that's what you would see as an object approaches the infinitely hot cosmic horizon. But if you followed information as it approaches that horizon, you would flow right on past, and then you'd realize you can't get back to our observable universe. The expansion of space-time is faster than light there. So that from your perspective, if you follow the information outside of the cosmic horizon, then it is lost from our universe. That's cosmic complementarity. So that is how Leonard Susskind and Gerard de Hooft saved the principle of information conservation. Now I want to go into a few of the details of string theory. So these fundamental threads of energy, that there's the 10 to the negative 33 centimeters. So the analogy that Susskind uses is that it would be like, compared to the size of a galaxy, one of these threads would be the size of a tree on the surface of Earth. So, you know, how much smaller than us, than the scale that we're used to, are these strings? Well, it's the same scale difference as the size of the galaxy, which is enormous light years across, compared to one tree on the Earth. So these are extremely tiny, too small to see. You can't create wavelengths of energy small enough that creates more energy. You would need an accelerator the size of the galaxy, 1 trillion barrels of oil a second to fuel it, in order to create wavelengths small enough to perceive these fundamental threads. So they're empirically unobservable, which opens string theory up to all kinds of suspicions that it's not science, it's philosophy or theology or whatever it is. It's not a part of empirical science. So that's one of the problems it has to face. So another part of string theory that has some suspicion on it is that it assumes that there's more than 3 dimensions of space. We have 3 dimensions of space and 1 of time. They're fused together in space-time according to general relativity. String theory requires that there are 6 more dimensions of space curled up at each point of our 3-dimensional space. So we have up, down, left, right, backward, and forward. That's 3 dimensions of space. There's 6 more according to string theory. According to Susskind, there's more than 6 in some versions of string theory. I'm just going to stick with what Susskind says in his books, The Cosmic Landscape and The Black Hole War. These extra dimensions of space are curled up at the smallest measurable, or the smallest, the Planck length is what they're curled up at, this tiniest 10 to the negative 33 centimeters. There are these little non-Euclidean geometrical shapes called Calabi-Yau manifolds. Xing-Tung Yau is one of the mathematicians who came up with these geometrical shapes, and as we'll see later, he was also a fan of Plato's, and he compared this theory of these extra dimensions of space being curled up at each point of 3-dimensional space to Plato's dialogue, the Timaeus. But and Leonard Susskind said these geometrical shapes are the DNA of string theory, because the fundamental threads wrap around those tiny curled up dimensions of space, and the way they do, that the shape of those extra dimensions of space with the strings vibrating around them, that is what accounts for all of the different particles in the standard model of quantum mechanics. So a photon is simply a string wrapped around these twisted shapes of space one way. An electron is a thread wrapped around these shapes in another way. So everything is made of threads, and the analogy is like a violin string. So all the notes on the musical scale can be drawn from a single violin string, and similarly, all of the particles in the standard model of quantum mechanics can be drawn from these fundamental threads. And the reason they are manifesting in different vibrational modes is because of the way they wrap around these extra dimensions of space. Also, in the quantum vacuum, this creation and annihilation of virtual particle-antiparticle pairs causes these fundamental threads, according to Leonard Susskind, to stretch out all the way across the universe. And the essential point to keep in mind for the book Psyche and Singularity is that all of the information is conserved at the outermost horizon of the universe and projected in with these threads. The reason that that is so important is because Carl Jung had a near-death experience in 1944 where he said he felt as if his consciousness rose above his body, rose above the earth, 1,000 miles above the earth. And in the end, it seemed to him as if the past, the present, and the future were interwoven at the cosmic horizon, and each of us in the 3-dimensional world, we live in our own little box of illusion, which is attached to that illusion creating horizon by a thread. And Carl Jung worked with one of the founders of quantum mechanics, Wolfgang Pauli, for whom Leonard Susskind has great respect. He says he's one of the best theoretical physicists of the 20th century. Carl Jung and Wolfgang Pauli, for 25 years, tried to develop a theory that the laws of physics and the laws of psychology must mirror each other because mind and matter both emerge from the same source, which they call the unus mundus, the archetype of the self, the God archetype, and the one. And I, in the book Psyche and Singularity, am saying that this gravitational singularity has all of the qualities of this unus mundus, the original psyche, and that's the equation psyche equals singularity. So that, I think, is a good enough background for the laws of physics that led up finally to string theory, how it got there, why they came up with this idea of information conservation at the cosmic horizon. And so now the next videos, the next few videos in this series will be going over parallels between holographic string theory and ancient philosophies of the self. So I went over the history of the gravitational singularity. Now I'm going to go over the history of the concept of a self. And that will stretch from the Vedanta philosophy of India, specifically the Vishnu-worshipping school of Vedanta, the Vaishnava Vedanta cosmology, then to Plato's cosmology, then to St. Augustine's cosmology, because St. Augustine synthesized Plato's cosmology with the Bible, and that created the Catholic cosmology that lasted for 1,000 years through Dante. And then I will cover Dante, and then after the Copernican revolution, when Catholic cosmology fell into doubt because the Earth was no longer seen as the center of the universe, the philosophies of René Descartes, who tried to come up with another non-biblical reason for believing in the immaterial self and God, then David Hume, the British empiricist who rejected Descartes' reasonings, and then I'll finally go over Immanuel Kant, who tried to synthesize David Hume and Descartes' thinking, where he came up with the ideas of the a priori categories of thought, which finally Carl Jung took to the next level in his theory of the archetypes of the collective unconscious. So in the next video, we will be comparing holographic string theory to the Vaishnava Vedanta cosmology of India.